Hello! Today I'm going to talk to you about an extremely useful graph theory tool called complement graphs, or complementary graphs. Now, we're only concerned with simple graphs for today, which we will define in terms of a vertex set and an edge set, just like that. Now, our complement graph, which we denote with a little dash, is equal to our vertex set, and then our edge set, what we do is we consider the complete graph on the same number of vertices, and we remove the edges from our initial edge set. And as you can see, we denote our new edge set once again with that same little dash. So as a first example, if we consider this graph here on 4 vertices, and you can see I've explicitly stated the vertex and edge set. Now ask yourself, what is the complementary graph? Remember, we want to take our complete graph, in this case, the complete graph on 4 vertices, and then remove the edges in our graph G. So, let's start. We have our first vertex, it's connected to only V4. So V1's only connected to V4. That means in our complement graph, V1 is connected to V2 and V1 is connected to V3. Now, V2 is once again only connected to V4. So in our complement graph, V2 is connected to V1 and V3. Note that it was already connected to V1. Now, for V3, it was previously connected to V4, so now it's connected to V1 and V2, already done. V4 was connected to all 3 vertices, so in the complement, it is isolated. That means our new edge set can be written just like this. We have V1 to V2, V2 to V3, and V1 to V3. Remembering that we are dealing with simple graphs, so the edges are unordered tuples, and we can change the order as we please, and the edge stays the same. Now, let's move on to another example. Consider first our cycle graphs. Here we have cycle graphs from 2 to 5 vertices. In our first case, right, C2 is also K2 or P2, and as our 2 vertices are connected, in our complement, we remove our only edge, and in fact, that is the complement of C2, already done. Now, here for C3, let's start with this vertex in yellow, right? It is connected to both of our other vertices, which means that, once again, our complement graph is a bunch of isolated vertices and is already done. Now we're up to C4. Ask yourself what happens this time. Take our yellow vertex. This time it's not connected to every other vertex, so we'll have to actually draw some edges. Our complement graph will look just like this, where opposite edges are not connected. So in our complement, we join the opposite edges and leave the rest out. Now for C5, here we go. Let's draw in only the missing edges for the complete graph. And that's our complement for C5. It's that star. Now, if you're familiar with regular graphs, or you've already watched my video on that, keep them in mind as we go through the rest of these examples. Let's look at our complete graph. Well, there's really not too much to discuss, because if I start with this vertex and I try to draw an edge, I'm going to see that I have got all 3 edges already drawn. So the complete graphs are both going to have complements which have isolated vertices. So we move right on. here we have some paths, right? You can see in this first one, our complement. It's right there. Now, next one. Let's start with this vertex. You can see that it's not connected here. Oh, wrong pen. Not connected here or here. Now, let's go on to our next vertex. You can see it's not connected here or here. Now, our vertex in yellow, when we go to draw it, we're going to see that it's already been connected right here. Oh, I have one extra edge. That makes more sense. Well, what is interesting about this one is we've actually gone on and done the exact same graph, because if you imagine taking this vertex and moving it over here, and you take this vertex and you move it over here, right, we will end up back here with the same graph. So the complement of P4 is once again P4. Now we consider P5. I'm going to take this vertex in red first, going to go across to here, as well as here and here. Now the yellow vertex is connected across to here and here. Now we go green vertex, already done one connection, just missing that one there. Our purple vertex, right? We have two connections which you've already completed, and then last one is already done. So that's our complement for P5. Now, if you're good at your visualization, what you can do is you take one graph, you take the complement, and you overlay the two, and you should hopefully arrive at a complete graph. That's easiest to see, in my opinion anyway, with these paths. So, if I take this graph and I overlay it with this graph, you can see that I end up with the complete. The same thing can easily be seen with P5 and P5's complement, but when I overlay them, I get K5, right? Which you can see we're just here, K5 and K4 respectively. Now, if I move on, the next one we're going to look at is our bipartite graphs. See if you can already predict what our complements for bipartite graphs will look like. Have a think. Remember, we're going to be drawing the connections which we do not have in our original graph. So, if I attempt to connect this yellow vertex with any other vertex in the complement, you'll see the only option is the one within its grouping. Right? Remembering for our bipartite graphs, we can draw two separate disjoint sets of vertices. Right? Similarly, for our blue grouping, this is the only one we can draw. Now, let's move on to the complete graph of 2 and 3, right? For our bipartite graph, complete bipartite graph. Hopefully, you can predict what's about to happen. For our red grouping, we have the exact same thing as before. For our blue grouping, we're going to connect those two vertices, we connect those two vertices, and then we mustn't forget that last edge there. Then, no surprises here. For K33, we go ahead and draw just like this for our complement. Now, last one, our favorite example, the Peterson graph. Have a think. If you attempt to visualize the complement for the Peterson graph, I'm going to forewarn you, there are more edges than you might expect. There's quite a few. Because this corresponds to, if you imagine I have my complement and the Peterson graph and I want to overlay them, that's the complete graph on 10 vertices. So, have a think. What do you expect? Furthermore, if you're familiar with regular graphs, what do you think we can say about the regularity of the complement of the Peterson graph? Remembering that the Peterson graph is 3 regular. Alright? Now, the Peterson graph is 3 regular, has a vertex set consisting of 10 vertices. So we take our vertex set, we remove 3 from the count for the 3 regularity, and then remove 1, which refers to the point itself. We can see that each point will have degree 6, which means that the complement will be 6 regular. And as you can see, I checked very carefully, hopefully I haven't missed one, the complement of the Peterson graph. It's a little messy. Yeah. That's it. Hopefully, you are now familiar and reasonably comfortable with the idea of a complement. As you proceed further through these videos, keep complements in mind. So when you hear about dominating sets, independent sets, colors, regularity, think about what the complement will look like. Anyway, thank you.